So what's the trend in the first ionization energy? Uh, if you look at the elements in a periodic table, okay, this is a table of the first ionization energy. This is helium, hydrogen right here. Okay, this is in electron volts. So hydrogen's around somewhere between 10 and 15. That looks like 13 point something, and then around 25 there for helium. So it's increasing, going from left to right in your periodic table. Okay. Lithium, second row elements here, you go from lithium to neon. The general trend you can see is also increasing. So in any given row of your periodic table, okay, the element or the atom with the highest ionization energy is the atom on the far right, the noble gases. Okay, so in any given row, the element that has the highest ionization energy would be the noble gas. Now, if you look at top to bottom, what happens? Within a given group, okay, let's compare, for example, sodium and potassium. Okay, so sodium's right here, potassium's over here, all right, lithium's right here, hydrogen's right here. So within a given row, within a given column, a vertical column, it decreases. Let's look at helium to neon to argon, so decreasing from top to bottom. Okay, so top to bottom, it's decreasing. Left to right, it's increasing. Or another way you can look at it, you can say it's increasing, increasing towards helium, okay? Increasing bottom to top, increasing left to right. So the top right corner of your periodic table, the atoms there would have the highest ionization energy. All right? But note, if you look at closely at this general pattern, you see there are exceptions here and there. So if you go from beryllium to boron, you see a drop. You go from nitrogen to oxygen, there's a slight drop. Okay. Generally, when you're going from group 2A to group 3A, you're seeing a drop there because you're going from a 2s, in this case, to a 2p subshell. So when an electron is in a 2p subshell, it will be a little easier to remove. We'll explain that in a little bit more detail later. Okay, so, and here in the case of nitrogen, you're going from a half-filled subshell, 2p3, and the valence configuration for oxygen would be 2p4. You're going from a half-filled where your electrons are in separate orbitals, parallel spins, and you're going into oxygen where you have an extra electron that would have to pair up with one of those unpaired electrons. So that would lead to extra repulsions on the outside among the electrons, would make it a little easier to remove the electron. Remember, ionization energy is a measure of how hard it is to remove an electron. The harder it is, the higher the ionization energy. Okay, let's look at this one. Which of the following has the highest ionization energy in the period where it belongs? Remember, a period is a horizontal row. Is it neon, sodium, bromine, or manganese? Okay, what did we say the trend was in ionization energy? It's increasing that way, increasing that way. All right, so you move to the right. Going up to the right, it's increasing ionization energy. All right, but look at this question. It's just saying in the period where it belongs. That means for every period, okay, in period 2, in period 1, row 1, helium has the highest ionization energy. In row number 2, neon has the highest ionization energy. In row number 3, argon has the highest ionization energy. In row number 4, krypton has the highest ionization energy. So the answer to this question is neon. Okay? Clicker questions here. Which of the following has the highest ionization energy? Is it sodium, rubidium, or nitrogen? What's the trend? It's increasing towards the right, right? So it's increasing that way and that way. So it's increasing this way and that way, the general trend. So you say sodium would have the high, nitrogen will have the highest ionization energy of these three.